Up to this point, I think we've laid a pretty good foundation or a good groundwork for understanding the climate system and some of the backstory for now adding in this sort of final piece of understanding what it is that we mean by global warming, what the phenomenon is, what its sort of cultural history is, and then especially to understand as well this panel called the Intergovernmental Panel on Climate Change from the UN, which issues these reports from time to time, which are in many ways the sort of definitive picture of where we stand with climate change. And anytime these reports come out, there's a whole media flurry. News agencies pick up on them, politicians pick up on them, politicians on both sides of the debate here, and they pick it apart, they tear it apart, they quote it, they use it to sort of forward their arguments. So I think it makes a lot of sense for us to be, as we sort of come out of this class, to have a good understanding of what the IPCC reports are, sort of what they say, and how to read them, how we can read them as sort of critical thinking individuals and get our information directly from the source rather than having it sort of filtered through all the various media and political channels as we so often do. So, some signposts to guide our lecture for this particular unit. First, let's talk about the sort of history of anthropogenic global warming. And what I want to do with this is to, of course, talk about some of the underlying science, of course, how we know what we know in the context of how we know that the Earth has sort of gotten warmer in recent years and what that looks like in sort of the larger perspective of time here, but also to talk as well about the cultural history, I guess you could say, of anthropogenic global warming as well, because it's a phenomenon, it's a topic that's really been surrounded by a lot of differing opinions and a lot of debate over time, and some different scientific ideas as well, although, we sort of move towards every day towards greater and greater consensus among the scientific community. So I want to talk about sort of both those pieces there. Then we'll look at the geography of changes in future projections, because like anything, we're not expecting a world that is going to be impacted in any sort of simple way or in any kind of uniform way. There will be different impacts in different places, different changes in different places, and I want to talk about what some of the challenges and opportunities are associated with that from place to place. And then, of course, understand what these future projections are. We oftentimes hear about future projections when it comes to climate change, what the temperature of the Earth will be like in 25, 50, 100 years, what that might do to sea levels, all of these kinds of things. And so we're going to take some time to look at what the different future projections are, and of course to understand how we come up with those future projections. And then last but not least, we'll take a closer look at the IPCC, Intergovernmental Panel on Climate Change reports, and I've asked you to read portions of the executive summary of the most recent report as well. So what I'd like to do with this is to just kind of give you a background, give you some of the tools, and walk you through a couple examples so that when you do read the report on your own, or as you're reading through the report on your own, the sort of language that they use makes sense, the way that they present information to you makes sense, and you can sort of parse through it and make sense of it on your own. So let's look at this phenomenon of anthropogenic global warming, look at its history and sort of where these ideas come from. I ask you to read a chapter out of Mike Holmes' book on the left there, Why We Disagree About Climate Change. And the chapter that I ask you to read is really about the history of the idea itself. Less about sort of the science of climate change and the physics of climate change, but really to sort of delve more deeply into understanding where this idea comes from. Because what Holmes sort of outlines in that chapter and what Spencer Wirt outlines in the book here shown on the right, which we didn't read in this class, but also another good book, is of course that it took scientists, it took historians, it took others, philosophers, a while to come around to this understanding, first and foremost, that climates would even change over time. And they talk about Louis Agassiz, who is the sort of famous glaciologist in Europe in the early 1800s, who first sort of outlines the idea that there could have been an ice age in the past, and that many of the landforms that are visible in Europe, in the Alps and parts of northern Europe, may have been sort of carved. They may have been erosional features from these massive sheets of ice that would have existed in Europe 10, 18,000 years ago. Before that, people didn't really have an understanding of what the forces were that would have shaped the environment, would have shaped the landscape in such dramatic ways. And so Agassiz's ideas about the most recent ice age are one of the first big pieces that come into play here. And this is only about 200 years ago, that sort of first gets scientists and others thinking about the fact that climates could change over time and could change quite dramatically over time as well. And I've concluded a link there to Spencer, kind of a companion to Spencer Wert's book here, which is sort of a timeline of the discovery of climate change. And it talks a lot about how it was sort of the key events, it is a timeline, of the discovery of climate change. First, that climate could change, that it could change, by natural forces. And then sort of secondly, that there may be these anthropogenic drivers of climate change, which is going to come into the picture much later in the 20th century, the second half of the 20th century, really, these anthropogenic drivers that are actually leading to the climate warming. Because, of course, climate change is sort of just a term that describes climate changing over time. And we know that the climate of the Earth and the climate from place to place has changed over time, and it's changed quite dramatically over time. And when we talk about global warming, this is a term that's more oftentimes used to describe what we sort of learned in the second half of the 20th century, is that there is this sort of anthropogenic cause for increasing temperatures and for warming temperatures that's largely related to greenhouse gases being emitted into the atmosphere. So you can take a look at Spencer Wert's timeline there, which is interesting, I think, to sort of put this into context to the larger sweep of time and to understand how we came about to sort of have these ideas in the first place, because it was not a sort of simple thing. It's kind of a long and winding road, really, that involved a number of different folks describing ways in which the climate could change, and there being a lot of pushback to these ideas initially within the scientific community and elsewhere, because they sort of seemed so radical, or they seemed so dramatic, the idea that there could have been, an ice age and massive glaciers that covered big pieces of North America and Europe, and to sort of see how scientific community and the general population sort of comes around to this idea, and now, of course, takes these ideas to more or less be fact in understanding how climates have changed, sort of dramatically over time. Another interesting piece to this is if we fast forward here in time quite a bit and we come up to the middle to latter part of the 20th century, the 1970s in particular, is to look at how scientists and others sort of imagined the future climate being, and how they imagined, if they were to project the climate out, what they would have sort of guessed the climate would be in 25, 50, or 100 years from any particular point in time. And I wanted to sort of bring this to your attention because this idea about the world sort of entering a period of global cooling is something that is oftentimes put forward by particularly some global warming skeptics and others as a sort of counter argument to the sort of more or less scientific consensus that suggests that there is anthropogenic global warming happening. And this was, of course, the idea that was sort of put forth in the 1970s by a number of different scientists, that we might actually be entering a period of global cooling going into the future. And folks who sort of put this theory forward, no doubt would have suggested that, in 40 years' time, by our time essentially here in 2016, the world would perhaps be a cooler place or a colder place. And this was sort of being put forth and sort of being picked up on by some popular media outlets. Time magazine did a couple of stories on this, and elsewhere you saw this in other magazines and newspapers as well, the idea that we might be entering a sort of period of global cooling, or that we might be going into another ice age, another period of glacial maxima. And, this wasn't just sort of media fascination with this idea, because if you look at the sort of longer sweep of geological time in the Pleistocene, of course, we've had these periods of glacial maxima and glacial minima, glacial ice expansion, glacial ice contraction, and we're currently in a period of glacial ice contraction. And all other things being equal, if we didn't have anthropogenic global warming, then it would be a safe bet to suggest that going into the future, we would probably experience another phase of global cooling and maybe a period of glacial ice expansion. And so, as I said, many sort of global warming skeptics, climate skeptics today have pointed to this and have said, well, all these scientists today are saying that we are headed towards a warmer future, a world of global warming with anthropogenic caused warming. But back in the 70s, all the scientists were saying we were headed toward a future of global cooling, of this sort of snowball Earth idea, or a period where the temperatures would at least be, half a degree or a degree colder. And there certainly were folks that were saying this, but what's sort of been revealed, what's been shown, is that even in the 1970s, there were more scientists who were suggesting that we were headed towards a period of global warming than there were scientists suggesting we were headed towards a period of global cooling. So there have always been different ideas. There's always been a bit of a debate, about the nature of climate change within the scientific community. And in the 1970s in particular, it was, sort of the voices that suggested we might be heading towards a period of global cooling were a bit louder, because there weren't as many people yet talking about this phenomenon of global warming. And so the graph that you see here is interesting because it was produced specifically to kind of counter these claims that all the scientists in the 1970s were saying we're headed towards a period of global cooling, and now everyone's changed their tune and they're saying we're heading towards a period of global warming now. And what they're showing here is that yes, there were folks who were talking about this global cooling phenomenon, and there was kind of an increase of peer-reviewed papers that were published in the 1970s compared to the 1960s related to global cooling. But if you take a look at the graph line there were always more papers published talking about this phenomenon of global warming and projecting that we might be headed towards a warmer future. And then, of course, by the end of the 70s, those who had been talking about global warming far outnumbered those who were talking about global cooling. And of course, if we look at the sort of numbers today, it's vastly skewed in the direction of global warming. So this was a graph that was sort of trying to address that argument or sort of counter that argument, although there were people who were talking about this sort of phenomenon of global cooling in the 1970s, but it's sort of most likely kind of overblown by those who are sort of skeptical of global warming, of anthropogenic global warming today, even though it did kind of capture the imagination of some people in the popular media in the 1970s. So elsewhere, in the larger debate about climate change, looking back at the past couple of slides, we have this sort of long history of sort of scientific work that has to happen for us to really wrap our heads around, to even be able to understand that there could be vastly different climates in the past and that climates could change from time to time. There was certainly some debate or some discussion about sort of where we were headed in the 20th century, in the middle part of the 20th century, in the 1970s, about a future of global warming or a future of global cooling. And of course, there have been also alternative explanations put forth for why we are experiencing warming today. And one of those explanations is, of course, that what we're seeing today is not being driven by anthropogenic causes. It's not being driven by anthropogenic emissions of greenhouse gases, but in reality, it's being driven by other kinds of forces, other natural forces. For instance, natural changes, natural fluctuations in the amount of incoming solar radiation hitting the Earth coming from the sun. And again, this is an argument that some folks in the sort of skeptical community, or some folks that sort of take an alternative view from the scientific consensus here, have put forward this idea that the warming that we're seeing in recent years may in fact be being driven by fluctuations in the sun's incoming solar energy and increasing amounts of solar energy that have sort of driven temperatures upward in most recent years. And those folks have oftentimes pointed to this period of kind of the late 1990s into the early 2000s, where if you look at the bottom graph there, the measurement of the sun's energy, you see that there's kind of these predictable peaks and valleys there. And then right around the year 2000, late 90s into the early 2000s, there is this sort of increase in temperature. And of course, increase in incoming amounts of solar radiation. And of course, this is a time when global warming, or discussions about global warming, are becoming very heated. Okay, you knew I would have to use that word, right? Pun intended. And politically and scientifically. And we do see temperatures that are sort of on the increase at this particular time, as you look at the, as you can see in the graph above there, showing global average surface temperatures right around that period of 2000. And so some people were saying, well, what we're seeing really is temperature increases that are being driven by the sun, driven by increasing solar radiation coming into the Earth, and not anthropogenic causes like emissions of CO2 and other greenhouse gases. The Royal Society, which is the scientific society in the UK, and the National Academy of Sciences, big scientific society here in the US, have released a report, or a couple of reports, sort of designed to address some of these sort of prevailing skeptical claims or counterclaims to the kind of scientific consensus on this. And this is one of the claims that they've sort of taken on, to sort of understand what role has the sun played in climate change in recent decades. And they acknowledge, of course, that there are these changes in the amount of incoming solar radiation because the sun's sort of solar output fluctuates. But they have sort of shown kind of conclusively, I would say, that it's not likely that it's changes in solar radiation alone that are causing the kinds of changes in temperature that we see today. And the reason why they're suggesting this is they point to two things here, two key pieces of evidence. One is, of course, that we see fluctuating solar radiation over time. And we see this kind of predictable pattern. But if we sort of graph out the temperature over the same period of time, we don't necessarily see temperature correlating that closely to changes in incoming solar energy. We really kind of see this sort of generally increasing trend line in temperature over this period of about 30 years shown here, whereas we see this sort of predictable up and down trend line with solar radiation. And so one thing is they're saying, the fit's not that great. The correlation really isn't that great. It doesn't seem like there's much of a correlation there at all, let alone, a causation. The other thing that they point to, the other piece of evidence which is critical here, is that they note that while temperatures in the troposphere have been increasing, temperatures in the stratosphere have not been increasing. In fact, have been decreasing slightly. The greenhouse effect occurs primarily in the troposphere, almost exclusively in the troposphere. If temperature were being driven by incoming solar radiation, the Royal Society and the National Academy are saying that we would also see temperatures increasing up in the stratosphere as well as in the troposphere because that radiation is passing through the stratosphere. and they're saying that it doesn't really make sense that we would see sort of stable or decreasing temperatures in the stratosphere while experiencing increasing temperatures in the troposphere. And because the greenhouse effect occurs exclusively in the troposphere, it would make sense, therefore, that the greenhouse effect is what's really driving temperature increases in recent years and the temperature increases that we're seeing in the troposphere. Now remember, the greenhouse effect is an entirely naturally occurring thing on the surface of the Earth, a naturally occurring effect that happens within the troposphere. And it's pretty well understood. It's essentially, scientific consensus is out on this, that there is a greenhouse effect and that there are particular gases that tend to be drivers of the greenhouse effect, or what we call greenhouse gases. These gases that tend to absorb and then re-emit solar energy within the troposphere, making for a sort of habitable world. And we have been able to show that there is a correlation, that there sort of always has been a correlation between greenhouse gas concentrations in the atmosphere and temperatures as well. So what you're seeing here is CO2 concentrations being mapped onto temperature back projections as well. And of course, you all know how it is that we can have a record of CO2 concentration in the atmosphere going back 400,000 years. This is from the Vostok Antarctica ice core. Remember those ice cores, layers of ice in Antarctica that have built up, and they're miles thick, that have built up over hundreds of thousands of years. Those air bubbles trapped in the ice contain basically samples of the atmosphere at different particular times. And so when we drill down into the ice, when we get these ice cores, we can look at those ice bubbles and we can actually look at the gaseous content in those ice bubbles and come up with an understanding of what the composition of the atmosphere was at those different times. Okay, obviously that's review. We talked about that in a previous presentation. What they've done here is they've mapped out changing CO2 concentrations in the atmosphere, parts per million volume. Okay, that's the line on top, the graph on top, the red line. And then they've also gone in and they've graphed out temperature. And of course, you should be asking, well, how do they get temperature changes going back in the past? Because of course, one of the critical proxies that they use are ice cores themselves. But what they've done here is used, other proxies as well. So sort of marine stratigraphic cores and other kinds of sediment cores to try and come up with a proxy for temperature. And they found a pretty close correlation here that the two map onto one another pretty well, in that when we experienced warmer temperatures in the past, we oftentimes had greater CO2 concentrations in the atmosphere, so more greenhouse gases. And when we had cooler temperatures in the past, we had lower CO2 concentrations or fewer greenhouse gases in the atmosphere. And this should make sense, this should make intuitive sense if we understand the greenhouse effect to work the way that we think it does, and that we would see varying levels of greenhouse gases that correspond to temperature over time. Okay, so we can go back 400,000 years and we can see these natural, for lack of a better term here, we know how complicated that word is, but these sort of non-human caused fluctuations in CO2 concentrations in the atmosphere. And we can see how they map pretty closely onto temperature fluctuations, temperature changes as well. The other piece to this, of course, is understanding how greenhouse gas concentrations have increased substantially in the last 50 years, 100 years, 150 years, especially, in how these concentrations have, in fact, really even eclipsed the concentrations that we saw over that time scale of the last 400,000 years. So over the last 400,000 years, we saw these sort of high points of of greenhouse gas concentrations at their highest, being somewhere in the sort of 350, 375 parts per million. And of course, today we're seeing them much higher than the past. So the other piece to this is to ask ourselves, of course, well, why are greenhouse gas concentrations? Yes, they fluctuate over time. They've been fluctuating. We know that from the Vostok ice cores and elsewhere for the last several 100,000 years. But why are they so much higher today than even those high points over the last several 100,000 years? And of course, the story here, or what's being shown here, are those increases in greenhouse gases. Remember that there are a number of greenhouse gases. Carbon dioxide is not the only one, but carbon dioxide having the sort of highest radiative forcing component, being the gas that in terms of its concentration and its sort of molecule for molecule properties is sort of the number one culprit here for being responsible for warming, that these gases have increased in the atmosphere over the last couple hundred years. And you can no doubt look at that and you can map that pretty well onto the Industrial Revolution, into the sort of speeding up of global economy and global economic production over the last 100, 150, couple of hundred years here. You're seeing two different scales there. You're seeing parts per million and for carbon dioxide and for, parts per million for carbon dioxide, parts per billion for nitrous oxide, and then parts per billion for methane as well. So that's why you're seeing the two different scales there. But nevertheless, showing those, both of those, all three of those gases increasing in concentration over the last couple hundred years. And, where, in particular, for the carbon dioxide, for the CO2, where does that come from? Well, here's yet another graph showing that there's a pretty strong correlation in those massive increases of CO2 in the atmosphere that we've been seeing over the last 100 or couple hundred years, correlating pretty closely to the increased emissions of fossil fuels, fossil carbon. In this graph, really showing it since 1900 and especially since 1950, sources like petroleum, coal, natural gas, cement production, and the sort of millions of metric tons of carbon being emitted every year into the atmosphere. And so that's what we're seeing here, anthropogenic sources of CO2 being emitted into the atmosphere. So we take a variety of this data and we sort of put it together here and we look at CO2 concentrations for the last 800,000 years. Again, able to go so far back in time using ice cores largely to get our sort of CO2 concentration in the atmosphere going back 800,000 years here. And of course, we see those fluctuations, right? We see those fluctuations, but then we see the sort of 2008 observed level of CO2 being substantially higher than any of the high points that we saw in the last 800,000 years. So again, a suggestion being made here that the CO2 levels that we're seeing in the most recent years are reflecting an anthropogenic signature, anthropogenic burning of fossil fuels, and that, of course, those fossil fuels putting more CO2 in the atmosphere, and that CO2 being a major driver of the greenhouse effect and sort of increasing the greenhouse effect and increasing warming. What they're showing here is projections for the year 2100 based on sort of a lower emission scenario and a higher emission scenario. If everyone agrees to cut CO2 emissions, we might be somewhere like 550 parts per million, but if we don't get any agreement, we might go all the way up to 900 parts per million that they're suggesting here. So in 2008, this number was almost 400 parts per million, probably like 380 parts per million or something like that. And I don't know the numbers today, but I think that we are right around 400 parts per million in our CO2 concentration, so quite a bit higher than at any time that we've been in the past 800,000 years. And last but not least, this is the graph showing CO2 concentrations and global temperatures. They've sort of created a baseline global temperature there, which might be like 57.5 or a little bit more than 57.5 degrees Fahrenheit. The temperatures are being shown per year here, going back to 1880 when we have decent temperature records in some places. The red bars, of course, are departures from the sort of average that are warmer than this average period, and then the blue bars being departures from the average that are colder. Late 1800s, early 1900s, we saw generally these cooler temperatures, which might correspond roughly to this period of the Little Ice Age that we saw in Europe, or Europe and North America kind of coming out of that Little Ice Age. Middle part of the 20th century, we see some years that are warmer than the average. We see some years that are colder than the average. And of course, since about the 1970s, since 1980, all of our years have been warmer than that average. And sort of, if we put the trend line on there, we kind of can see an increasing trend in temperature. And then, of course, this is being mapped out with CO2 concentrations as well to sort of show those show the correlation between CO2 concentration and increasing temperature. And again, just to sort of reiterate a point from a couple of presentations ago, what we are seeing here, therefore, we're seeing these greater CO2 concentrations in the atmosphere and other greenhouse gases. We know that there is a greenhouse effect, a naturally occurring greenhouse effect. We can see how increased levels of greenhouse gases in the atmosphere lead to warmer temperatures over time. We can see all of this stuff in correlation. And again, remember, we're not necessarily calling carbon dioxide a pollutant here. It's a naturally occurring thing within the Earth system, within the various spheres of the Earth system. What's perhaps more fitting to describe it, what's sort of a better way to understand this, of course, is a kind of anthropogenic intervention into what is an otherwise sort of naturally occurring carbon cycle. And what this graphic is showing is, it looks kind of complicated, but it's really just showing these different spheres of the Earth, right? We have the ocean, we have the biosphere, plants and soil, we have the atmosphere, and we also have these sort of fossil deposits. And it's showing sort of total amounts of carbon stored within those different areas. And we can see that in the ocean, there's massive amounts of carbon stores that are being held in the ocean. And then all those different arrows are just measurements of transfers, right? The carbon cycle, carbon cycling throughout the different spheres, showing how carbon moves from the biosphere to the lithosphere to the atmosphere to the hydrosphere, and showing different arrows, just trying to show you kind of general amounts that are moving back and forth here. Of course, what humans have largely done through the use of fossil fuels is to dig carbon out of the lithosphere, or to pump it out of the lithosphere, dig it out in the form of coal, or pump it out in the form of oil, to then burn it and then release carbon in the form of carbon dioxide up into the atmosphere, where we know carbon dioxide functions as a greenhouse gas, and to sort of overload the atmosphere with carbon dioxide and therefore sort of increase the greenhouse effect. So something that occurs naturally, but of course humans in many ways intervening in the natural carbon cycle and intervening in a way to transfer carbon out of the lithosphere, out of these fossil deposits, and into the atmosphere. And of course, the challenge there being that this warmer climate that it is likely causing, the global warming effect, is going to have impacts, of course, on the way we live our lives. It's going to have impacts from place to place. So according to the IPCC, sort of the authority here on climate change, most of the observed increase in global average temperatures since the mid-20th century is very likely due to the observed increase in anthropogenic greenhouse gas concentrations. There you have it. When the IPCC says very likely, this is not just a qualitative descriptive term. This is a term that's actually tied to a sort of probabilistic measure of the likelihood of something being true. And we'll talk about that in more detail towards the end of this presentation. But the IPCC for several years now has been sort of very clearly, kind of unequivocally equating the increases in greenhouse gases that we've seen since the mid-20th century with anthropogenic causes. And of course, one of the ways that they have done this is they have sort of modeled temperature rises since the year 1860 or so. And they did something very interesting. They took all of the sort of natural forces that drive climate change, so things like changing solar radiation, natural fluctuations in greenhouse gases, the things that we see happening with Milankovitch cycles. And what they did is they put in all these natural factors, and they took out any kind of anthropogenic factors from the climate system in these models. Okay, these were hypothetical models, and they ran the models with only these sort of naturally occurring climate factors, these sort of naturally forcing factors only. And that's the graph that you see in the top left there. And what they did is they ran the model and they said, okay, based on all these natural forces, what does the model suggest would happen with global temperature over time? And what you see there is, from 1900 to about 1950, the model is pretty close to the actual observed temperatures. But then take a look at what happens after 1950. After 1950, the model is saying, okay, based on the natural factors, you would expect to see a temperature sort of slightly on the decrease. But of course, what we've seen is a temperature that has continued to increase and increased really kind of quite dramatically since 1950. And then what they did is they said, okay, let's plug in only the anthropogenic factors into the model. And then let's map that on to the observed temperatures over time and see what we get. And it's actually kind of curious there because you see in the early part of the 20th century, it does map pretty closely there, but around 1950 there's kind of a difference. The model is saying the temperature might have been cooler, whereas the temperature was actually a bit warmer. But what agrees pretty well is the projection of this sort of latter part of the second half of the 20th century, like the 1970s to 2000 there, where the model projection maps pretty closely onto the observations as well. And so then what they did is said, okay, well, let's plug in the natural and the anthropogenic factors, and then plug that into the model and see how closely that correlates with the actual increases that we're seeing in temperature. And they saw in that sort of bottom graphic there a pretty strong correlation between what the model says should happen and what the actual observations of temperature are. So in this way, they were, in some ways able to kind of isolate the variable of anthropogenic warming factors, of anthropogenic climate change factors, and show that there's a pretty strong driver there, that anthropogenic forcing is a pretty strong driver there. And of course, when we put in the natural factors as well, we see a pretty close fit between the model and the observations over the last 100 years or so. Okay, so there you have it. That is the evidence, really, for anthropogenic global warming, for anthropogenic climate change, for anthropogenic factors being the driver of temperature increases that we've seen in recent years. It's always so interesting to present these factors because I think, increasingly folks are coming on board with this or having an understanding of this. Like this likely isn't the first time you've heard this. It likely is not the first time you've sort of seen some of these graphs or you've heard these ideas expressed before, because they're becoming fairly ubiquitous within the media and within the news outlets and in sort of popular scientific outlets as well. It changes over time, and that's really interesting to see. It's interesting to see the kind of consensus emerge about this, but of course we'll talk about what some of the kind of more contemporary challenges are and what some of the contemporary debates are sort of about this data and about the kind of narrative of climate change in the next lecture. Okay, so as with everything in this class, we're going to take a look at the sort of geography of changes and also sort of try to understand what these future projections suggest about temperature and about what the impacts might be related to climate change and anthropogenic global warming going into the future. Take a minute to explore this article from the National Geographic on rising sea levels and how they might impact low-lying islands. It's a really interesting article that came out fairly recently within the last couple of years. And of course, what they're saying here is that obviously low elevation islands, places like the Maldives in the Indian Ocean, are potentially going to be, threatened quite a bit by rising sea levels. A sea level that rises, by a few centimeters can make all the difference on an island nation that is itself, only half a meter above sea level. It can make a huge difference in low-lying areas. It can make a huge difference, when storms come through there, when hurricanes, when typhoons come into these areas, just making the storm surge that much more dramatic. And in some cases, there may be islands that are just completely submerged by rising sea levels. Now, the interesting thing about this is that what this article suggests is that, our understanding, arguably, of island topography, of island geomorphology, is pretty incomplete as well, in that there have always been changes in sea levels over time, and it hasn't necessarily meant that sort of every island just sort of disappears, that the water simply rises and then it covers the land. And in fact, what they're showing here is that in some other cases, in the case of Tuvalu here, that the island itself sort of responds to changing sea levels. And you'll see some interesting graphics showing that, how the sort of configuration of the land itself is changing over time in relation to changes in sort of the levels of the ocean and levels of the sea. Of course, what they suggest ultimately is that that's an interesting thing that we might see happening in islands with really low population densities or islands where people don't live there, but in places where people have sort of developed these islands where there are towns and cities, that's a whole different story, because you can't simply just change the settlement geography of these places. You can't just simply move these high-rise buildings very easily back from the coastline or to a different island altogether. So it's a kind of complicated story that sort of reaffirms, I think, what makes intuitive sense, that rising sea levels are going to threaten many of these low-lying island nations, but that there may be also a more complicated picture here, and that the sort of geomorphology of these islands changes and has always changed in relation to rising sea levels. Well, if we go to a much more different sort of climate type here, moving farther north into Greenland, here's another National Geographic article for you to explore. which looks at climate change and how it has impacted and how it's projected to impact Greenland's ice. Of course, ice cover in the northern hemisphere has really dramatically been impacted by rising temperatures in recent years, and particularly in places like Greenland. Greenland has seen, a big decrease in its volume of ice on the continent there. Of course, Greenland mostly covered still by a massive sort of ice sheet that covers all of the island, but that ice sheet is sort of shrinking. And in another article here for you, another important article, also from National Geographic, this sort of adds the human element to it. Unlike for those folks in low-lying island nations like the Maldives, there's folks in Greenland who are not concerned, and in fact are looking forward to a future of rising temperatures. And what they're saying here is that there's also, people sort of dreaming of greener fields and greener pastures, maybe, access to new oil reserves that were once locked underneath the ice, ice-free waters for navigation, you name it. And of course, what they're referencing here, too, with this idea about Viking weather is the medieval warm period. And the idea that Greenland was sort of settled and colonized by Vikings in the years right around 1000 AD, at a time when the temperature may have been a bit warmer, making Greenland a bit more hospitable, and that perhaps we're going to see a return to that kind of weather with global warming going into the future. So you can take a look at that article, sort of skim through it, read through it more carefully if you'd like, to see what folks in Greenland are saying about the potential changes related to global warming. As I suggested, we're seeing big changes happen in the northern hemisphere vis-a-vis temperature, and leading to decreasing amounts, decreasing volumes, decreasing extents of ice in the northern hemisphere. We're seeing this in mountain glaciers. We're seeing this in continental ice sheets, or in ice sheets that exist on land, as in the case of Greenland. And we're seeing this in the Arctic sea ice cover as well. So the Arctic Ocean, most of the year, is covered in ice, still is, although that ice extent has been decreasing sort of dramatically over the last several decades. This is the observed change in the area of Arctic sea ice over the course of the 20th century, largely. And what they're showing there, really since the 1970s, this trend of decreasing ice in the latter part of the 20th century in the Arctic. And of course, it makes sense that with increasing temperatures, we would see decreasing ice. But of course, the other thing that's happening in the context of the Arctic and in the context of Greenland as well is what's called the ice albedo feedback effect. And what this is saying is that, perhaps one of the reasons why we're seeing ice decrease at such a rapid rate in the northern hemisphere is not just because of warmer temperatures, although of course warmer temperatures are probably what's driving this, but all the other feedback mechanisms that are associated with those warmer temperatures. And one of those is the way that albedo decreases here. So think about it. Think back to our discussion about land use cover and land use change. We talked about the sort of cascading effects of land cover change. Well, there can be a kind of cascading or compounding effect of change with ice loss as well. So it's not just that there's warmer temperatures sort of melting the ice, but as that ice recedes, it exposes darker colored rock, in the case of these continental sheets, or darker colored water, or water that has a different sort of specific heat value. And whereas ice and snow has a very high albedo and reflects lots of incoming solar radiation, that exposed rock, that water, those darker surfaces have lower albedos and they absorb more incoming solar radiation. So the ice albedo effect is suggesting that temperatures increase, melting back the ice, revealing surfaces with lower albedos, which just absorb even more solar energy and cause even more heating, even more warming, and cause the ice to recede even faster. So there are a number of different factors, part of these feedback loops, that sort of work together to sort of have a compounding effect in causing decreasing amounts of sea ice or decreasing amounts of sort of continental ice sheets in the case of Antarctica. This is another chart here showing the 1990s, showing the decreasing Arctic ice extent over this time period. So this is showing summer ice limits. Okay, so during the summer season, the extent of ice, and the ice, of course, is at its lowest extent in the summer season in June, July, and August. But what they're showing in the 1990s, in just 3 years, in 1996, we saw a much larger extent of sea ice, and then by just a couple of years later, a much sort of smaller extent of sea ice in the northern hemisphere. Okay, we're going to add a piece of evidence in here that seemingly contradicts the narrative. In this is that in contrast to what we've seen in the Arctic, in the northern hemisphere, in the Antarctic a couple years ago, 2014, we saw Arctic or Antarctic sea ice reach its record maximum extent. And of course, you should be asking, well, what's going on with that? I thought we were in a sort of period of global warming, and here we see ice in Antarctica reaching its maximum recorded extent. We've never seen it become so big. And I've included a link here for this NASA site, which talks about this. You can click on that, you can watch the video. Talks about how Antarctic sea ice has sort of reached, it's a big, massive extent, its sort of largest extent in 2014. And there have been some climate skeptics who have, of course, pointed to this and say, well, how does this jive with the narrative of global climate change? It doesn't seem to jive at all. And the first thing really to understand is that we have much less understanding of Antarctica, arguably, and the sort of context of climate in Antarctica than we do in the Arctic and the Northern Hemisphere. So in many ways, the scientists, and if you watch this video, they're quite honest, about saying, well, we don't really know exactly why we are seeing ice reach, a maximum extent in Antarctica, or sea ice reaching a maximum extent in Antarctica. Perhaps it's just a fluke, and we're going to see it decrease. But nevertheless, this is what we're seeing. This is what we're observing. We can't deny that. A couple of things here. What we're seeing is a maximum extent of sea ice, not necessarily a maximum extent of the continental ice field in Antarctica. Of course, Antarctica is a continent. There's land there, and you can sort of see the outline of the land of Antarctica, and there is an ice sheet on top of the land there. There's an ice sheet miles thick, right? That's where our Vostok ice core comes from, these other ice cores. We're drilling on the continent of Antarctica through the ice down miles thick. Surrounding Antarctica, there is also sea ice as well. And so in the southern hemisphere winter, which would be, June, July, August, September, that ice reaches a thick maximum extent. So the ocean itself freezes in that case there. And so we're not necessarily saying that the continental ice field is reaching its maximum extent or its maximum thickness. We're really only talking about sea ice here. So there is a distinction there. And the other thing that the scientists point out in this video is that the sea ice maximum in Antarctica is by no means compensating for the sea ice minimum in the Arctic. So the amount of ice that we've seen lost in Greenland, in the Arctic, and elsewhere is not equal to the amount of ice that's been gained in Antarctica or in the sea ice of Antarctica. So on the balance, there is a net loss of ice globally. The sort of maximum extent in Antarctica is interesting. We're trying to understand why that is, and it might just reflect, a difference of climate impacts from place to place, but it doesn't necessarily make up for the loss of ice elsewhere. Now, you've no doubt heard of climate projections being made into the future, and people saying, well, if business continues as usual, we can expect global temperatures to increase by 1 degree Celsius over the next 50 years, and this might have an impact on sea levels, by increasing by melting of continental glaciers, of continental ice fields, might have an impact on sea levels by increasing sea levels by 2 centimeters, 3 centimeters, 6 centimeters, what have you. One of the ways that they are coming up with these projections are through the use of what are called general circulation models, or GCMs. And these general circulation models are the models that we use to try and understand climate change impacts going into the future. And they are extremely complicated models because they have many different variables. As this graphic suggests, they have many different variables that you have to plug into the model. And then each of those variables is impacted by the other variables. So as we discussed in the case of the ice albedo feedback loop in the Northern Hemisphere, you can't just plug in temperature as, a variable that is independent of all the other variables. In fact, there really is no independent variable here. They're all sort of moving with one another, and they're all sort of influencing one another as well. So you have to account for that as well, which makes these models extremely complicated, and which makes them, in a practical matter, require just enormous amounts of computing power in order to run them. And so the models, of course, have gotten better as the technology has gotten better, as computers have gotten more powerful, and we can crunch more numbers, we can crunch more variables, we can plug more variables into the system. And these general circulation models, of course, have been critiqued, and people have said, well, can we ever really model something as complicated as the climate? And that's a valid critique, something to think about. But of course, we are getting better and better with these models, and the technology is getting better. And so, our models are better, and they're much more robust now than they were 5 years ago, than they were 10 years ago, than they were 20 years ago, than they were 30 years ago, for sure. And of course, what we can do with these models too, to calibrate them, to sort of see if they're any good, is to see if they can predict the past climate, and see if they can predict the past climate well enough. And so we plug in the factors that we know to have existed, say, in the 1960s and the 1970s into the model, and then we see how good the model is at projecting back in time the climate of the 1960s, for instance. And this is how we calibrate them. This is how we see if they're any good. This is how we see if they're worth their salt, is if they can predict climates in the past. And if they can't do it that well, we say, this model's probably not that good. We need to keep working on it. If they can do it, if they can do it well, and if they can do it consistently, we say, okay, we might be onto something here. Let's sort of proceed cautiously using this model and see what it tells us about the future, plugging in a variety of different variables and a variety of different values for these different variables. So, just as scientists know paleoclimates through a variety of different methods, including ice core analysis, scientists know or make these sort of future projections based on these sort of highly complicated general circulation models, which are being used to model what might happen in the future, both globally and regionally from place to place. Okay, last but certainly not least, let's take a look at these IPCC reports and see what it is that they tell us about climate and the current state of climate knowledge. So the IPCC is on its fifth assessment report now. They've been releasing these for the past few decades, really. They seem to release one once every 5 to 7 years. And now we're on the fifth assessment report. And the idea really is to give us a baseline, to give us a kind of clearinghouse of scientific knowledge regarding the issue of climate change and sort of where it is today. So each time one of these reports comes out, there's just a magnitude of more scientific information. There have been more studies that have been done, past studies that have been verified or that have been sort of thrown out, new ideas that are put forward. It's sort of meant to be a representation of kind of the cutting edge of sort of where we are and a synopsis of where we are with climate change science. So the IPCC is a project of the UN largely, and there are many different scientists and countries and academic institutions and others that are involved in contributing information and in terms of, and in putting these reports together every 5 to 7 years or so. This is an interesting chart here. This is just a summary in the assessment of scientific findings, just showing how there really is a proliferation, or there's more and more scientific papers, more and more information being put out there about climate change. And so this is showing the past few decades, and by region, sort of which regions, scientists in those regions are sort of releasing papers about those regions. And so you can see where most of the information is coming from, which is, absolutely skewed towards the Northern Hemisphere, and as you can see, skewed towards North America, Europe, and to some extent Asia there. Sort of much less being produced in South America and Africa and elsewhere in the Southern Hemisphere. But nevertheless showing a general increase in the kind of scientific papers that are being released over time by these different regions. And what I've done here, by the way, is I've included page numbers for where I've sort of pulled these screenshots, these graphics. So as you're reading the IPCC, you can go to these pages, you can reference the PDF presentation here if you want to have sort of more information to sort of get the backstory about what you're looking at here. A couple slides ago, we had the piece of information from the IPCC saying that greenhouse gas concentrations are very likely due to anthropogenic causes. And I mentioned that this term very likely actually is associated with a sort of probabilistic likelihood of the thing occurring. So throughout this report, the IPCC uses these terms like virtually certain, extremely likely, very likely, likely, and these are not just merely descriptive terms here, all right? They're not just descriptive terms of how we might use them in everyday speech, but these are actually associated with a very particular probability of that thing have happened or happening in the future. And so this is important because oftentimes we sort of hear the media repeat these terms, but we don't really understand why it is the IPCC uses those terms and what they mean in terms of the actual sort of probabilistic measure that they're assigning to them. And so the IPCC really has this scale, this probability scale, this likelihood of something happening based on these terms are actually based on a sort of percentage of probability. The other piece here in the sort of matrix that you see on the top right there is they also have an assessment for the amount of agreement there is for a piece, for a finding, and the robustness of the evidence. And so the gold standard, of course, would be that there is high scientific agreement on something and that there is robust evidence. And that would put you in that sort of top right box there. High agreement, high evidence. And so claims that are being put forth can be measured. And so what the IPCC is saying is that, look, folks, this is something in which there is not only good, robust evidence, but there is high agreement among the scientific community about this particular thing being true or this particular thing having a strong chance of happening. On the other side of that scale, there would be low agreement and less robust evidence. So this would be something where, there's not much evidence out there, and there's not much scientific agreement either about sort of why it's happening. And so things that fall into that box most likely don't even get mentioned by the IPCC because there's a lot more research that needs to happen before that can become part of the sort of IPCC's clearinghouse of information. But nevertheless, not only do they present information, the IPCC, but they have measurements for sort of how certain we are about the probability of it being true or the probability of it having have happened or happening in the future, and also the amount of agreement there is, scientific agreement there is, and the amount of evidence that there is as well. So they have a whole variety of ways for parsing out and for understanding, really, the evidence that exists and the discussion within the scientific community as well. So they're not just saying, like, scientists say this, but they're saying, here's where scientists have high agreement with high evidence and high probability, and here's other things where science is not agreeing, where there's sort of low evidence and we don't have a good probability associated with it yet. So certainty, evidence, agreement, probability, these things are key, and it's important for us to understand that there are different levels here when the IPCC talks about these different things. And so you put it all together into this summary view here, which is presented on page 42. Now, oftentimes, this is all the politicians see. This is all the media sees. And they want a soundbite. They want, a sort of clear finding. They want to be able to say in that news story or to their political constituents, that the IPCC says that global warming is causing more forest fires in Arizona. And instead, what the IPCC is saying is that in the context of forest fires, for instance, there may be a driver there from global warming, but there's lots of other factors there as well, and so we need to be careful about the claims that we're making in terms of forest fires in Arizona. Of course, media and politicians oftentimes don't really like that nuance, and like I said, they're looking for the conclusive sound bites. But this is an interesting map, I think a really effective map for showing complicated information, but in a relatively simple way. And it takes a minute, I think, of looking at this to understand what they're showing here. Of course, it's a map, so you're seeing things, a geography of changes here, region by region, North America, South America, Africa, etc. And what you're seeing here is the extent to which these physical systems, biological systems, or human and managed systems are being impacted by anthropogenic climate change. All right, and so what you're seeing there is a sort of color coding for physical, biological, and human. Okay, so that should be pretty obvious, and we see things like, glacial ice extent, or, wildfire, or food production. And then what you see, though, is either a darkened symbol, a colored-in symbol, or an outlined symbol for each of those different elements. And this is sort of a quick reference. The darkened symbols, the sort of filled-in symbols, are things where you are going to see a major contribution of impact coming from climate change there. The outlined symbols are areas where really all they can say at this point is that there is a minor contribution of climate change causing the impact for that particular system. So that's an important piece to it. And then over here on the left, of course, we also have this confidence scale to where they're saying we can assign a confidence in understanding the attribution that's being caused by climate change for any one of those particular phenomenon. So let's look at North America, for instance. We look at North America, we look at that sort of summary box there. We have physical systems in blue, and we have glaciers, snow, ice, and Arctic permafrost. And what they're showing there is that those physical systems, the cryosphere of North America, there's a major contribution. The changes that we're seeing in ice extent in North America, so the receding mountain glaciers, the warmer winters, the reduced snowfall, all of these things that we're seeing occurring in North America, that's a filled-in symbol there. So they're saying that there is one of the major reasons why we're seeing that change in snow and ice cover in North America is because of anthropogenic climate change. Okay, it's a major contributor here. And in fact, we have high confidence that the main driver here, the main factor that's driving the change, is coming from anthropogenic climate change. So it's not, urban heat island effect. It's not a natural change in wind patterns or something like that. It's not some sort of natural change in albedo or solar radiation. What they're saying here is pretty conclusively that we have lots of evidence and strong agreement, and we can say pretty confidently that the changes that we're seeing in snow and ice cover in North America in recent years, that change is being driven by anthropogenic climate change. They got high confidence of that. Conversely, though, if we look at biological systems, we see that wildfire is one of them. Okay, now wildfire is an outlined symbol only. So what that means is that, yes, we're seeing changes in wildfires. If we look particularly in Arizona and in the American West in the last couple of decades, boy, we've seen a greater frequency of fires and we've seen a greater intensity of forest fires in the American West and in other parts of North America as well. However, what they're showing here is that we can't really say that there is a major contribution to forest fires that's being caused by climate change. So there likely is a minor contribution here, and if we have warmer summers, for instance, that is probably going to be contributing to the intensity of fires and the size of fires, but we don't have the confidence to say that that's the number one driving factor in the changes that we've seen in forest fire intensity over the last few decades. And so it's an outline symbol. And not only that, but our confidence in being able to say that there is an anthropogenic climate change driver that's causing some of the changes that we see in wildfires in North America, it's actually only medium. We're not even high with that. So there's a chance that the changes that we're seeing in wildfires in the American West might not have anything to do with global climate change. Now, a lot of folks have suggested that there is probably a contributing factor there, but there are other things happening with wildfires as well, including, not the least of which, the way that we've managed forests historically. We've fought fires before, which has led to a massive increase in the buildup of fuels in forests, and so they tend to burn more intensely. So, the way that we've managed forests, is a big driver as well of causing the change in wildfires that we see in North America. And a number of other things are major contributing factors to that. So what they're saying, in the case of North America, the changes that we've seen in snow and ice cover, yeah, we can attribute that to climate change, big time. The changes that we've seen in wildfires, probably some contributing factor there, but, don't get ahead of yourself, media. Don't get ahead of yourself, politicians. It's really hard for us to say that there is a major driver there in wildfires that's coming from climate change. At least it's hard for us to say at this point. And a lot more study is needed before we can kind of say conclusively one way or the other, the extent to which that global climate change is driving wildfires. So you can do this from region to region, from place to place. You can look at the extent to which their confidence in the attribution is high, and to whether or not there's a major contribution coming from climate change, or whether or not there's a minor contribution coming from climate change. And all in all, sort of the critical thing here, because the IPCC is not just interested in producing scientific information for the sake of having scientific information out there, but of course they want to, hope that there is going to be an impact on policy. Hope that there's going to be an impact on governmental policy, on ways that we sort of respond to this, on management policies, on the things that we do. So a big piece of this that they show on page 37 is the kind of risk matrix, or understanding the risk flow here. And what you're seeing there is, climate factors on the left, socioeconomic processes on the right, all feeding into this kind of overlapping Venn diagram of vulnerability, hazards, and exposure, which is all part of your risk, which is being driven by impacts, which is also being driven by emissions as well. To put it simply, it's all connected to everything else that you see here. Everything is sort of impacting everything else. None of these variables are really independent. The impacts are dependent on socioeconomic processes and natural climate and anthropogenic factors and emissions, and our exposure to the hazards and our vulnerability, our risk, all kinds of things like this. Ultimately, our risk from climate change varies, and it varies for a whole bunch of different factors, including where we are geographically. Do we live in Greenland, and do we see global warming as being something that's going to be positive for us? Or do we live in the Maldives and we see global warming as something that's going to be negative for us because increasing sea levels are going to flood our island nation? Do we live in a wealthy country, which will most likely be well situated and easily able to adapt to a changing climate? Or do we live in a poorer country with fewer resources, where people are already kind of living in poverty, on the edge of poverty, and any change in food production or any change in climate might have massive cascading impacts throughout society? All of these things are part of this sort of larger risk matrix, these different factors that lead in to helping us understand what our risk is ultimately due to climate change. And as you could, of course, can already piece together for yourself, this is not going to be a risk that is shared equally among all the individuals and all the groups and all the different countries in the world. Some places, no doubt, will be impacted more heavily by climate change, and other places will be impacted less heavily by climate change, and some places might even see big advantages associated with climate change, Greenland being one of them. Okay, so this was a longer presentation, I realize that, and a lot of information packed in here, but I think important for us to sort of understand these different pieces of the puzzle to kind of make us more informed, better able to contribute to this debate, this sort of larger debate about climate change, and to some extent to be able to get the answers for ourselves by looking at the IPCC reports, by understanding some of the underlying science, by understanding some of that underlying history associated with climate change, and how we've come to know that the climate can actually change. Okay, in the next presentation, the last presentation, we'll take a look at some of the narratives, some of the debate, some more of the sort of social piece of the puzzle of climate change.